Okay, so this is where we'll continue from taking from the last video. So, of course, one thing I want us to observe is for those of us that have the notes from class, you see that they had wrote this before this. Guys, it doesn't mean, okay? It's addition. You can write this before this. It's just that when I was writing it, I know these two are what we have inside the bracket for Green's equation. So I just wrote it down. I didn't really memorize the order because the order doesn't really mean. So let's just continue. All right. Now, what we are trying to please ensure you watch the last video before watching this one. Okay. So what we are trying to achieve here is this. We are trying to bring this particular guy what out to have it as this equal to something, 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 something. Do we understand? Do we understand? Remember the last video I said, by the time if we know the source current, then we are going to do what? Can know this one, and then this, and then electric and magnetic field. Okay. Now we have assumed that, according to what we have in our notes, assume that if we know the source current, now how do we achieve what the magnetic vector potential for any of the components, which is x component, y component, or whichever component? How do we achieve that? That's why we brought in Green's equation. Okay. Now, note that this guy, this value is hidden or is together with what? A second order differential equation. Remember, nabla means what? Partial, partial. X plus partial y and partial z, which is of course square. So okay, you have that on top for all of them. Now so since this guy is attached to a differential, we want to separate it. And how to separate it out to have it as this equal to, you use what? Green's equation and Green's function to help us out with that. So since we now have this expression, hold on. Since we now have this expression and this expression, what we'll do next is like that quadratic. Do you remember simultaneous linear equation? Where you have one equation, you have another equation. Okay, you have two equations with what? Two unknowns. Let's say A and B. Two unknowns equal to something. Like simultaneous linear equation where you will now use elimination method. You use the coefficient of this to multiply this equation. Okay, you use from this equation to multiply this equation. You use from the linear equation, that elimination method. If you know that, then I shouldn't even be explaining deep into what we want to do now. However, if you don't know that, well, that's okay. So what we'll do now, since we are trying to bring out this particular guy, what is the, looking at this expression, I think I wrote something in the last equation. Let me do that again. Okay, let's just continue. So take this one. Are you seeing this green, which is the G? Then you see this one, A hat X. These are the two guys. So you use this one. How do we know those are the two guys? Of course, look at it. This is grains, right? You see beta, this. Okay, these two things, you also have them here. Okay, so the difference, we are looking at the left hand side, please. The difference between this side and this side is what? The AX and the what? The G. So use this one to multiply everything in equation 1. So that will now give you what? Use this to multiply everything in equation 1. Then for this one, use everything to multiply everything in equation 2. Of course, I and I. So this multiplying everything here will give us what? Okay, so what we have here, I just rewrite the whole thing, the same thing. And this is what we have on top already. I just erase. Oh, okay. Okay, so same thing. After that first multiplication, which is this multiplying the top, you have this one right here. Okay, then that's this ax multiplying this other one, you have this guy under here. Now there are a few things I want you to observe. This, you see this guy, when it multiplies what we have on top, instead of writing g of all this, we just wrote only g. Okay, so g multiplies this thing, gives you this, plus g multiplies this one, gives you this. Okay, then g multiplies this one, gives you this. Hope that's clear. Then ax multiplies this one, ax multiplies this, gives you this. Okay, gives you all this together inside here. Observe, we also omitted this one, just wrote only g, because we know when we write g, we are still talking about g of all this. Okay, so yeah, that's why I put that arrow there. Then another thing to note, this guy is actually like this, a minus sign. That's why you have it as minus sign here. Yes, the small change, this minus this. Hope that's clear. Okay, it's at this part we have it as this guy, arrow, comma, arrow. Of course, bar, prime. Okay, now since we've done this is equation, I think that's equation 5 in our notes. That's IV. Okay, yes, that's it. Okay, and then this other one is equation I said IV. This is equation V, which is 5, Roman figure 5. This one is VI. All right, which is this. Now, if you look at the one in our notes, you will see a slight difference from what we have here. Okay, that is because what equation 6 here, what we have in our notes, they have multiplied it. That's this multiplies this. So meaning this multiplies this and this multiplies this. So what you now have is what? This, okay, plus this. That's what you have inside this place. Okay, look at what they have here. Okay, that's clear. Equal to the remaining parts. So let me just make that change now. Now what we have to do is to subtract. Okay, subtract this minus this. But we can also open this bracket so that they will look alike. This multiplies this multiplies this. So if we do that, we are going to have this times this will be what? Ax hat. Okay, then right? And then this will now be what? Okay, so these are the two. We are going to subtract this from this. Let me even erase this part. Okay, so if you do that, what will you have? All this minus this. Okay, so this will be what? What we have here is what? We'll have this, and then the minus sign. This one, that's this minus this. Okay. Well, this is going to be very long. It's going to fill this part. But let me just write. Let's see how far I can go. Then this is exactly, this is the same as this. Okay, these two are the same, so we'll cancel them. This is also the same, we can cancel them, but what we want to cancel out is this term. Cancel out this term. Why? So that we'll not have beta here again. So we have this present and it's also present here. So by doing this, we cancel out the beta term. So we know we are not dealing with just this guy and then this guy. Remember, what you are trying to achieve is this equal to something. That's what we are trying to achieve, huh? At this point. So so this is this minus this. This minus this cancels out. Then this minus this will give us what? Minus mu naught. No space. Let me just show you my notes, okay? So what we have, look at what I've written so far. Okay, this. Okay, Of course, the beta is out. Then equal to minus what I was about to write. Okay. And then plus, and then plus this, which is this one. Why plus? Because you have a negative sign here. You have a negative sign here, and then another negative sign outside the bracket. So minus minus gives you plus. So here you have what? A plus sign. Good. Now, after having that, there is another vector identity we use on this expression. Look at this expression. We use the vector identity saying that whenever I should, excuse me. Okay, now according to the vector identity, whenever we have this kind of expression, it simply means it is equal to, let me put it on that, it is equal to this guy now. You will now write it as what? This, sorry, you write it as what? You write it as what? This, and then you write this guy twice. But you put what? Dot there, telling you what? Divergent. Then you can now put this other one there. Okay? Then minus, do the same thing to this one. Write it twice, put a dot there, and then you put your G. So this whole thing is equal to this. Okay? So that's what we have right here. Can you see that? Then what they said, factorize the right hand side, which is this other part now. So meaning that, look at this guy now. Let me write it out so that, okay, so we can see this thing now. This thing which we've written out, like saying that this thing is equal to what? This expression. Okay, this thing we've written out saying that this whole thing is equal to this expression, right? Equal to this expression. So if you look at this thing now, this whole thing minus this whole thing, you can see that nabla dot is common. You have nabla dot here, you have nabla dot here. So you bring it out. Look at it, bring it out. And then what you have left inside will be what? These guys. Okay? When you remove nabla dots, when you have what? G, nabla, then A. Okay? Of course, this is nabla. Okay? That's nabla. Nabla dot, nabla. Okay? So nabla dot out, you have AX and nabla G. AX and nabla G. So that's what you have. So in this expression, bring it back to this, which is 6. All these guys now, all this place, you replace it with this one. So that's what you have. Excuse me. So that's what you have here. Look at this whole thing now. Instead of this whole thing equal to this, we have this whole thing, which is this, equal to this guy. I hope you can see that. Now, having this now, we can do what? Integrate both sides over a volume. Why are we doing that? Now, the idea here is this. Since we now have this equal to this, remember that we are trying to do what? Get what AX is. AX, what will be this? Is that not so? So what we do now, we'll now try to say, okay, what will the effect at different points? You have to do what? Use integration, because it's kind of sum. Okay, so you integrate over the volume. All right, so we are going to do that. And what do we have? We'll do that to both sides. Look at this and this. So you see this. Okay, everything here dv. This same thing, we just put integral sign v, then dv. The same thing to this other side. But of course, you have a plus sign. So integral here, or integrate here, integrate before the plus sign. After the plus sign, integrate again. That's what you have here. That's what you have here. You see, look at all these things. Of course, you bring this constant out. You integrate the source current there and every other thing, dv, then you put plus this other integral here and every other thing, then dv. Now, once you have that, you now apply what? Divergence theorem. Because that expression you have there, it looks like what? Divergence theorem. This is the divergence theorem, saying that S, that's saying that integral, uh, saying that the volume integral, okay, volume integral of the what divergence of a field is equal to what? The closed is equal to what? Surface integral, but of course closed loop. All right, of what? That field. Okay, multiplied by ds or dot ds rather. So, meaning we can now say what? This gives what? This expression here. So, look at this guy. We have all these things dots, right? So, it's like you're comparing all these things. Divergence, nabla dot all this, right? Look at it. Nabla dot f. So, what f is? This whole thing, dot f, you can write it as what? The closed loop, surface integral, of course, f dot ds. Meaning f is representing what? Everything here. So you can, instead of using volume integral, nabla dot this, you now use what? Close loop. Okay, surface integral. Where you have the f, look at it now. Where you have f here, you put what? All this there. Dot ds. Do we get it? And then the other side, of course, has their remain the same as this. Remain the same as this. Okay? Then for the radiating field in what? Unbounded free space, the surface integral vanishes at infinity. What I'm trying to say is that you have an antenna, and my funny antenna again. So signals going out. Now for an unbounded, look at it. For the radiating field, radiating field, okay? Radiating field. In unbounded free space, so there's no stop here. It's just like till infinity, okay? The surface integral vanishes at what? Infinity. So you are trying to sum up the effects or the electric field or the field, let me just say field, sum up the effects at different points. At infinity, that integral vanish, okay? Because this guy just keeps moving on, unbounded. As in no stop. I said unbounded. Yeah, no stop, like unbounded region. Keeps extending without limits. Okay? So at infinity, that surface integral does what? Equal to what? 0. Okay? So your surface integral of whatever tends to what? 0. Tends to 0. So meaning everything we have here will be what? Equal to 0. Look at it. Everything we have here will be equal to what? 0. So 0 equal to the rest things present here. Good? Hope we are following so far. Then our delta function, using the delta function, which is this, we do what? Everything equals to what? F of arrow bar. Now, how do we get the delta function? Look at it. Look at our delta function. This is the rule for delta function. You are not deriving this thing here. Just know that for delta function, you have this. So where f equals what? Ax. Look at our expression here. Okay, volume integral ax, and you now have the delta function dv. What they are saying now is that compare this thing, compare it to what? This. Look at the delta function, right? Look at the delta function. Look at ax. Look at f of arrow bar prime. What they are now saying is that whatever you have, comparing this to this, it tells you that what? F equals to what? Ax. Do we get it? So that means this whole thing you have here saying that volume integral of all this, look at it here, volume integral of all that, plus all this time you say what? Plus what? AXR. Do we get the idea? We have replaced everything here with just what? AXR based on the delta function formula. Good? Now, all we have to do at this point is just to do what? Pack everything you have here. Pack all this in, move it to the other side. So you have AX arrow bar equal to all this thing. Of course, the negative sign will disappear, so it will become positive. So you can now say AX arrow bar equals all this. That's what you have here. AX arrow bar equals all this. Okay, so now you can substitute the green function, because this is the green function now, G. So where you have G, you will now plug in, I say plug in, you will plug in what? What does that G mean? Look at it here. Look at it here. Remember I said the G, when we deal with the G, oh boy, great. So remember I said when you deal with the G, okay, you are talking about this whole function. So G equals all this. So where you have G in that formula, you put all this. Look at it here. Where you have G here, AX arrow bar equals this, this, this. Now, your Green's function, what do you have there? Where you have G, you have all these things there in place of G. Do we get it? Of course, dv. Okay? Now, good. Hope that's clear. Then, AX will now be equal to what? You bring this 4 pi, you bring it outside, you leave all those arrow inside, bring the 4 pi outside, so you now have this over what? 4 pi. So this over 4 pi. Of course, volume integral, this GS, look at it there, then this guy, look at it there, and then what? dv. This is your equation 17a. Now we've gotten what? AX. We've gotten AX. So just apply the same thing to what? AY and AZ. Just that anywhere you have the X, you put what? Y. For Z, you put Z. Just that. So 17A, 17B, 17C. I think my notes, I did not number the equations correctly because we are supposed to have equation 16 before 17. So maybe I missed numbering or something. Okay. So combining 17 gives the vector expression. So instead of writing AX, AY, AZ, just write A. The vector A equals all these things. I forget all those X and Z, all these things. Just write all these ones like that. This is the magnetic vector potential. Now we finally gotten an expression for it. Okay? So we finally gotten an expression for it. Look at now, from our notes, it says that in principle, if we know the current distribution, JS, which I think I've said something like this in a video before, JS. If we know that current distribution over the surface of the radiator, okay, or antenna, that's JS, we may find the component of the magnetic vector potential. These components, and these components, and these components, which we've done. Okay, and then what? And then, okay, magnetic vector potential from 17, equation 17, which are these, okay? And then what? From the Lorentz condition in 13, we have this thing. How? Where is? But look, remember, 17 is what? Giving us the magnetic vector potential. What about the scalar potential, which is V, our scalar potential? Remember, from equation 13, look at it here. This one, just make V subject of the formula by dividing by all these ones. So you have nabla dot A, which is the coil of the magnetic vector potential, the divergence of the magnetic vector potential divided by negative all these things here. That's what V is. So that's what you have here. Okay? Equals all these things here. Now we are having that square root. We are having that square root because of what? Because of this. Sorry, where's 13? We're having that square root because of our what? And J. Remember, J is what? J equals what? Alright? Square root of -1. That's what J is. Okay? So, when you have that here, of course, this is our minus sign that we already have outside. See that it's no longer there. Okay? It's no longer at the numerator, but it's on top, affecting this guy. But it doesn't affect this one because of our -1. Okay? Alright, so hope that's clear. So now you can substitute this into what? 8b to yield what this one will be. Remember, 8b is what? The expression for the electric field. Okay, 8b. Look at it. Look at what V is. V is right here. So the nabla V, and we've gotten V to be what? To be this one here. So you now say what? Nabla this whole expression here. Look at it. But you have a minus sign here. But based on this minus sign coming from the V, it cancels out and makes it become what? Positive. So that's clear. Now, yeah. So in this equation, V encloses JS and arrow is the distance between the different volume elements. That's the surface point. Okay. So, and the point at which we are computing A, that's the field point, as shown below. So in the next video, we'll start from this particular diagram here. Okay.